Okay, so let me recall where we were last time. We had seen the idea of encoding linear transformations between vector spaces. So T from V to W as a matrix A. So this relied on choosing bases for V and W. Okay. For V, W, and then we had this, in the notation, the way that we wrote it, we had, well, I'll write AV to mean the same thing as T of V, and what you do is you write V in terms of a basis, I'll write N, so this is V is alpha 1, E1 up to alpha n En for some basis Ei of V. And then the matrix A, so you obtained this matrix by writing the images T of Ei. I'll just write T of Ei were the columns of this matrix written in the basis, a given basis for W. And then there was this standard procedure of multiplying this matrix by this vector, or if you want, we know how to multiply a matrix by a n by 1 matrix, so that we produced T of V, and you took alpha I and multiplied that scalar by the ith column, and then you sum those from I equals 1 to n. Okay, so let me do an example which comes up in my area of research, topology, a good amount. So this is, we're going to do kind of a little version of it where you'll see kind of a first application of linear algebra to study geometry of certain spaces, or the shape of certain spaces. Okay, we've already seen that linear algebra interacts with calculus a lot, so that's not exactly true, but this will be of a different flavor. Okay, so we're going to start with a graph, gamma, okay, which is just going to be vertices and edges. Okay, so it's a collection of vertices, collection of edges, and their edges go between two vertices. They might go to the same vertex. I guess you can also have two edges going between the same one. That's fine. And we're also going to assume that these are labeled edges, so I'm going to give a direction to each edge. If you want to think of this as some sort of electrical circuit, and this is describing which direction the current flows, that's a pretty good intuition for what's going on. Okay, so that's what we're imagining, some sort of network where the arrows are kind of telling us which direction we're going to go. Okay, we're going to define two vector spaces. I'll just make them real vector spaces. You can do the same thing over the complex numbers. Okay, so the first one is, I'm going to call it C1 of gamma, and it's just r to the e. Okay, so in other words, this is functions which go from the edges to the real line. Okay, so there's the set of edges that I'm assuming it's some finite set, and they go to the real line. So a basis, or a natural basis, consists of the function, which I'll call Fe, which sends e to 1, so a certain edge e to 1 and all other edges to 0. Okay? So this is obviously going to be a basis. We call these the characteristic functions. Not that that's too important. Okay? And we do the same thing for the vertices. So we have C0 of gamma is r to the v. So functions on the set of vertices to r. Okay? And now there's a natural linear transformation which goes from the C1 to C0. Okay? So how do you define this? Well, I'll say what it does on a basis. Okay, so and I'm going to call it the boundary map. So you can think it takes an edge to its boundary. It goes from C1 to C0, and it takes an edge. So on the basis, remember that it's also, each edge comes with an orientation. So we're thinking of this basis as having a 1 on this oriented edge, and it takes it to the function which assigns 1 on one basis vector and -1 on the other basis vector. All right? And then we extend linearly. So this is this, magical procedure, or just a nice procedure, which means that so any function defined on a basis extends to a unique linear transformation. Okay, so namely, if I want to know what boundary does to any vector, so this is v, I write it in terms of my basis, and then I just send it to alpha 1, since I know what to do on the basis, alpha n boundary of vn. Okay? So this is certainly a linear transformation, just by the way that you've constructed it. Okay, so that's the map. All right? And what you should investigate, and we'll see more examples later on of this, but investigate what the boundary looks like for certain graphs. Okay, so here's a couple good examples. I mean, you can't make, this is another reason why it's obvious you want to consider high dimensions in linear algebra, right? Because here you just, the number of basis vectors depends on the number of vertices. So for an arbitrary network, these are going to be high dimensional. I'll just give you 3 examples. And so what is the boundary? And then does this tell anything about the shape of gamma? Okay? So we'll see it does, but it's good to just kind of work out on your own what is, to guess what's going to happen. Okay? So let's see. Oh, and maybe I should say, what is the matrix, right? This is what I really want, because we have a standard basis. Okay, so let me go to the kind of the main topic of today. Well, we'll see a couple. I guess we have two main topics here. So it's the composition of two linear transformations. Okay? So we have t, which goes from v to w. We need t prime, which goes from w to u. We can compose them. So we get t prime composed with t. This goes from v to u. And you can check that this is certainly going to be a linear transformation, right? So what we have to check is if you put in, well, t of alpha 1 v1 plus alpha n vn, okay, so some linear combination, then this is equal to, well, by the first, since t is linear, this is alpha 1 t of v1 up through alpha n t of vn, okay? And then since t prime is linear, it's alpha 1 t prime t of v1 up through alpha n t prime t of vn, and that's exactly what you want for a linear transformation. Okay, so now we'd like to, since we have kind of encoded these linear transformations as matrices, well, what we have, maybe I'll just say it like this, we have a matrix A, which goes from W to U, a matrix B, which goes from V to W, and notice, so we've had to choose bases for VW and U for this to make sense. I want to assume that the same basis to define A and B, the basis agrees for W, okay? So V and U, you kind of choose arbitrary bases, and then for W, you have to choose the same for both A and B, okay? And what we would like to define is a matrix C, which, well, it's going to represent this composition. So it goes from V to U, and we think of it as the matrix AB. Okay, so A multiplied by B is going to correspond, we're going to define the multiplication so that it corresponds to composition of these linear transformations. Okay, so let's see what this matrix is. So what is C? Okay, so first, well, we have to work out what the first one is. So what is B? Okay, so the columns of B correspond to the images of a basis for V. So maybe I'll say to the images T of VI. Okay? So we take, this is, written in terms of the W basis. Okay? So the columns of C, well, of course, they correspond to, you plug in VI into T prime composed with T. Okay, so that's what you see for C. Okay, so in other words, to find a column of C, we take a column of B and apply A. Okay? So we take a column of B that's precisely the image of a basis vector for VI. Here we're looking at the image of the composition. So you just, plug in this column into the matrix for A. Okay? Because that's going to give you T prime T of V. So there, in other words, we take A, to now the column vector T of Vi, and this is going to be the column that corresponds to C. Okay, and that's how we define our matrix multiplication of A and B, right? We just say that we're going to the ith column of the matrix AB is A applied to the ith matrix, the ith column of B. Okay? So let me do an example, all right, or a couple examples so we can see what's going on. So first example, I'll do 2, 1, 1, 1 squared, okay? So this is going to go from R2 to itself. Okay, so we saw before this linear transformation. Now I'm just going to do this linear transformation. Since it goes from R2 to itself, you can compose it an arbitrary number of times. Okay, so then you take 2, 1, 1, 1, and we're going to multiply it by 2, 1, 1, 1, okay, to get the composition. Okay, so how do we do this? Well, we're going to get a matrix. So I'll write this here. So we're going to get a matrix. The way you get the first column is you take the matrix 2, 1, 1, 1 and apply it to the first column of B, which is just the same matrix here. So what do we get here? Well, we know how to multiply these matrices, or we know how to take a matrix and input a vector. So this is 4 plus 1 over 2 plus 1, so we should get 5, 3. Okay, so this 5, 3 is precisely the vector, or the column, the first column here. Second column, you do the same thing. You apply the matrix 2, 1, 1, 1 to the second column, 1, 1. And then what do you get? You get 3, 2. Okay, so the square of this matrix is 5, 3, 3, 2. And you see what happens, right? If you look at 1, 0, under 2, 1, 1, 1, this goes to 2, 1. And then under 2, 1, 1 again, this goes to 5, 3. And that's exactly what this matrix is representing, right? This is the image of 1, 0. For the matrix squared. Okay, so let me do another example. Oh, maybe I should say, okay, yeah, let me put this in here. So note, AB only makes sense when we can compose the transformations. Okay, so you have to have, you have to have, if you're mapping from Rn to Rm, so we have Rn goes to Rm, goes to Rp or something, then obviously if I have Rn goes to Rm and Rq goes to Rs, I mean, this is going to correspond to a matrix multiplication which makes sense. And this one is not, because you can't compose these linear transformations. They have different, the range of this isn't the domain of this. Okay? So on the level of a basis, this corresponds to, let's see, so the number of rows of the first matrix should correspond, or the number of rows of the matrix B should equal the number of columns for the matrix A. Okay, this is just another way of saying Rm has to be the same in both cases. Okay, so let me do another example. Okay, so I'm going to write down the matrix for projecting onto a line. Okay. You could also do reflecting over an arbitrary line or a similar transformation, but this one's going to be slightly easier. Okay, so what the projection does, so I'm going to say, well, so I'm going to project onto a line through the origin y equals alpha x, and it takes a point and maps it to, well, it maps it to the closest point on the line y equals alpha x. Okay, so you get the whole plane projecting onto this line. So the way that we can actually define it, or certainly the way that we're going to compute this linear transformation, is we're going to compose as a rotation to the x-axis. Then we're going to we're going to project to the x-axis, and then rotate back. Okay? So I'm going to say it's, so the way that we got the rotation matrices were their cosine alpha, sine alpha minus sine alpha, cosine alpha. I think I'm going to be off by 2 pi or something here. So what I want is the angle here is going to be alpha. Okay, so I'm going to scratch that off. Okay, but this is the point. This is what I want to measure. So you're projecting onto a line, and the rotation angle from that line to the x-axis is alpha. Okay, so this is actually going counterclockwise. So what we want to do is first reflect this clockwise to the x-axis. So you get the matrix, oh, sorry, so I did get that right. Cosine alpha, sine alpha minus sine alpha. Cosine alpha is the clockwise rotation. Okay? Then we project onto the x-axis. Well, this is very simple to write with regard to the standard basis, right? So what you have is you take, one point, you're mapping it to the x-axis. So 1, 0 goes to 1, 0, and 0, 1 just gets killed, goes to the 0 vector, okay? So therefore our matrix looks like cosine, sine, and then 1, 0, 0, 0, and then we rotate back counterclockwise now. So we get cosine minus sine, sine, cosine. Okay? And now to figure out what this matrix is for this projection, and I should say this is what we're working out. Oops. We are working out the matrix in the standard basis. Okay, so we're seeing where the standard basis vectors go. Well, you do this matrix multiplication, so let's work it out. So first I'll do these two, okay? So I'm getting cosine minus sine, sine, cosine. And now, what does this matrix do when I multiply it out? Well, I'm first taking the 1, 0, 0 matrix and applying it to this first column. Well, it's easy to see that what you get is just cosine alpha 0, okay? So when I plug in, this 1, 0, 0, 0 matrix just kills off this term here. Similarly here, okay, so you can check that this is cosine alpha 0, and then sine alpha 0. Now again we do the matrix multiplication here. So we want to see what this matrix does to cosine alpha. This will give us the first column, and it's precisely cosine squared alpha sine alpha cosine alpha. The second one is, what does this matrix do to sine alpha? And you get exactly sine alpha, cosine alpha, sine squared alpha. Okay, so you can check these formulas easily. This is now the general formula for projection onto y equals alpha x. You can do a totally similar thing if you want an arbitrary reflection. The same procedure works. It's a little bit more complicated multiplication, but not very much so. Okay. So I won't write down all the properties. You can look in the book for, the properties of matrix multiplication. I mean, they are the same as a composition of functions. But you have to remember at some point that these are not just arbitrary functions, but linear transformations. Okay? So for example, matrix multiplication is associative. I've already kind of used that. And that's just because composition is associative. But it's also, okay, I guess I am going to end up writing a lot of them down. Since they're linear transformations, they satisfy, the properties that linear transformations satisfy, namely if you add two linear transformations and compose, it's distributive. Okay, so this is just properties that you get from composition of these nice functions. The main property that is, it's important and also a struggle, right, is that this process is not commutative. So it's not like multiplying numbers in a field. You have to worry about the order, right? And this is just, composition is not commutative, right? So for one thing, I mean, it's, AB might be defined and also BA might not be defined, right? So you can't just compose, if you can compose T with T prime, you can't compose T prime with T. So that's an issue. Even if they're both well defined, they still won't be commutative, right? Composition of functions is not a commutative operation. So this is what you're stuck with, okay? But, so it makes it harder or more interesting depending on but what you like, I guess, or who you are. So let me give just a kind of a definition which is useful to see, I think, and it kind of encodes this non-commutativity. Okay, so the commutator, which is usually denoted A and A commuted with B, is just AB minus BA. Okay? So in other words, the commutator is 0 if and only if A and B commute. Okay, so if they multiply and you get 0, or if you look at the commutator and you get 0, then AB is BA. Okay, so it's a useful way to measure, in some sense, how much certain matrices don't commute. If you have a very complicated commutator, then they really don't commute, and if the commutator is somehow getting simpler, then maybe they don't commute, but it's not too bad. Okay, so let me just do a fun example. Okay, again, if you want to practice up on your matrix multiplication, commutators are good things to compute since you have to compute two of them. Kind of the best example to look at, because it's relatively easy to see what the matrix multiplication is if you look at the matrices 1 on the diagonal, 0's everywhere except one matrix, non-zero entry n. So this is my matrix A, and my matrix B is going to be Ones in the diagonals m. Okay. Then what is the commutator? So you should check that A and B don't commute. And what do you get? So what is the commutator of A and B? Okay. So maybe I'll also write down, so the matrix 1, 1, 1 with all zeros, you can easily check, is called the identity matrix. And it's exactly an identity for matrix multiplication. So maybe I'll call this, okay, and so in general, this would be I3, in general it's IN, and you can check that A times IN, whenever this makes sense, is equal to A, okay, and vice versa, so IN composed with A. Okay, so these matrices aren't the identity matrix, they're close, but it ends up already from that you get non-commuting matrices. In general, it's kind of a large game, and we'll see a lot of this later. Given a matrix, what are the other matrices that commute with it? Okay. In other words, given a linear transformation, what are the linear transformations that commute with a given matrix? It's going to be an important problem for us. Maybe I'll mention, since we're talking about a multiplication, this will come up in the next lecture, but not every matrix will have an inverse, in the sense that A times A inverse is the identity. Okay, so again, it's different than multiplying elements in a field. And you should think this is a linear transformation going from V to W. We're asking for an inverse map. Well, I mean, for one thing, inverse functions don't exist unless the map is a bijection. That's going to have to be an assumption. And then we're going to want to say, well, we'll see that that's going to be equivalent to the existence of an inverse, but that takes some work. Okay? All right, so now let me talk about two more concepts. So now I'm going to switch topics slightly to talk about traces. Okay, so now we're going to assume that A is a square matrix. Okay, and its trace, so here's A, I'm going to write as A, ij from 1 to n. Then the trace of A is just the sum of the diagonal terms. Okay, so in other words, the sum from 1 to n, A, k, k. So it's easy to check that the trace actually defines a linear map. Okay, so it goes from, you can think it goes from n by n matrices to the real numbers, okay, or, complex, or any arbitrary field, okay? And this is a linear transformation, okay? You might ask, what's the matrix? Maybe this will be a good little exercise to do. Of course, there's standard bases for the space of matrices and for the real line, okay? So here's the main property, and this is something that I'm going to leave as homework, okay? So if you take two matrices, A and B, again, I'm just going to assume that they're square and of the same size. Okay, you can do a similar thing for n by m and m by n. Okay, but I'm just going to do this case. Then the trace of AB is exactly the same as the trace of BA. Okay? This turns out to be a really important fact. Okay, the proof is homework, and this is important. Okay, and it's something that it might take a while to realize its importance, but I'll give you a couple reasons why this is. Okay, so the first reason, just philosophically, is that this is an essentially unique operation. Okay, so in other words, if I have any function which goes from the n by n matrices to the real numbers, or again, the scalars in question, okay, which is linear, say f, and satisfies f of AB is f of BA, then f is like the trace, well, or is proportional to the trace. Okay, so you might take, okay, so you could be clever and do, instead of the trace, you could do twice the trace or something. But that's essentially the same thing. Okay, so it's important, well, especially because if you want any linear transformation which satisfies this property, you're stuck with the trace. So and then it kind of shows that it's some sort of fundamental object, right? There's just not many operations which satisfy the properties that it does. Okay? This also gives us kind of an easy, it shows that the trace is relatively easy to compute, which is good. Of course, this is not, just working out, if I have A, B, C, D, then spitting out A plus D is not the hardest operation in the world, right? I mean, we can all do this. On the other hand, if I just give you a random linear transformation and you want to write down its matrix and then take the trace, well, that can be hard, right? You have to work out bases and find the matrix. That's a bit more work, okay? In this case, it turns out that since the trace of AB is the trace of BA, you can always find the perfect basis, which makes the trace easy to compute. Okay, so let me just give you, I'm going to go for the last example. Okay, so this was matrix alpha, and we were projecting onto the line passing through the origin. Okay, and the way that we computed the matrix was by looking at, the rotation, so first you rotate counterclockwise in alpha, then we took the projected to the x-axis, and then, so at first we rotated clockwise to get down to the x-axis, then we projected onto the x-axis, then rotated back. Okay? And then what we ended up with, I'll just see if I can remember the formula, was cosine squared, and then a sine, cosine, sine, cosine, sine squared. All right? So then, therefore, the trace is 1. Once you've computed that matrix, it's easy to compute the trace. Okay? On the other hand, this would have been a much easier calculation if we only cared about the trace of this matrix. Namely, I could have written, say, A as rotation of alpha, B is projection composed with rotation, clockwise of alpha. Okay, then AB is the matrix we're interested in, but the trace is equal, So the trace of AB is equal to the trace of BA. But on the other hand, this is projection rotating minus alpha rotating alpha. And this just cancels out, right? This is the identity matrix. In other words, BA is just projection onto the x-axis. So it's 1, 0, 0, 0, and that's completely obvious to compute the trace. Okay? So what this is really, so anytime you have a matrix realized as they're in compositions, it's kind of easier to work out the trace. This is true more generally. What's the real phenomenon that's going on is that the trace is independent of the basis that's chosen. Okay? So if I have a matrix, or sorry, if I have a linear transformation which goes from V to V, and I choose one matrix and another matrix, so these are the matrices for T in two different bases. Okay. Then what will happen, it turns out, is that the trace of A is equal to the trace of A prime. Okay? So this is, there's kind of this unnatural thing whenever you want to work with matrices, that it depends on the basis that you're given, or that you have, you choose for a linear transformation. And this is saying that there's a quantity which is independent of that. Okay? So in other words, if I wanted to project along the line here, okay, well, I could have chosen a very easy basis. Okay? So there's an easy basis. Namely, I compute one of my basis vectors is on the line. The other basis vector is orthogonal, so it goes to 0. Okay? In this basis, the matrix, again, is just 1, 0, 0, 0, and you just see the trace is equal to 1. Okay? So if you're allowed to choose, whatever basis you want to compute some invariant of a matrix, it's often much easier to do, right? Because you can choose kind of exactly the right basis you need. Okay? So actually, maybe I'll just give one more little note on the trace. So the trace is 1 here. And notice we are projecting onto a line. Okay? If you do a similar characterization, say, of projecting onto a plane in R3, and you do a similar argument, then you'll see that in general, this trace, you can actually define the dimension of a subspace. So usually we think of dimension as somehow as the number of basis, or the number of vectors in a basis. Here you can do it without a basis, which is kind of nice, as just the trace of W as the trace of this orthogonal projection onto W. Okay, so this is just a little note. We haven't really shown all this, or really, I haven't defined orthogonal projection precisely. But this is just another useful aspect of the trace, and there are many more. Okay. So maybe now I'll just give a couple notes about the transpose, since it's kind of a natural place to put it. I know that we've seen, or you've seen this before, so the book has, mainly to save space, written a column vector, so x1 through xn as a column is the transpose of a row vector. Okay. In general, so if A is Aij is an n by m matrix, then a transpose is given by the matrix Bij is an m by n matrix where Bij is Aj. Okay? So if it's an n by n matrix, if it's square, then what you're doing is just reflecting the entries over the diagonal. Or in general, if you have something which isn't a square matrix, you're just turning every column into a row, and vice versa. Okay. All right. So as linear transformations, well, so A is giving us a linear transformation from V to W. Okay, again, you have to choose a basis for V and W for this to make sense. Then A transpose in the same, again, thinking of it in the same basis, since you've chosen bases for V and W, A transpose is a map that's going from W to V. Okay? So this is usually called the adjoint transformation. So this will come up throughout the course. Maybe I'll mention just some definitions here. So the linear transformation is self-adjoint if A is a transpose. Okay, so if the corresponding matrix is symmetric. Okay, so at the way I've said this isn't completely well stated, because it's not obvious that if you choose a different basis, that if you have a symmetric matrix for one, it will be a symmetric matrix in the other. This turns out to be true, though. Okay, and in general, you just say if you have a symmetric so A equaling transpose means So this means that A is symmetric. So a symmetric matrix just as A is A transpose. If A is negative A transpose, then we say A is skew symmetric. And we'll see there are other characterizations or other definitions involving these which will come up naturally later. So one example we've seen is that, when I took this matrix, or when I took this transformation which projected onto this line, again, we got a symmetric matrix out of this. Right? So cosine squared, sine squared, sine, cosine, sine, cosine. So this is a symmetric matrix. Maybe I should note here that skew-symmetric matrices have to have zeros on the diagonal, okay, since that's fixed by the flipping. And also these matrices, symmetric and skew-symmetric matrices, have to be square. So this is, anyways, if you have a symmetric matrix, there's no restriction on what the diagonal entries are, but of course these entries have to match up. Okay? And we could have also seen this in another basis as just the matrix 1, 0, 0, 0, which is also obviously symmetric. Okay, so maybe I'll just go back to the first example that I started with. So if we had this graph, something like this. This was our gamma. And then we had defined, oops. So we had defined this map, which goes from functions on the edges to functions on the vertices. Okay, so 1 here goes to 1 minus 1. Okay, so think about what is the transpose of this. Okay, so I'm going to think of this, I'm going to call it delta. Okay, so boundary transpose will be delta. This is now determines a linear transformation from the vertices. You know, you take a vertex or a function on the vertices and it's going to go to a function on the edges. So think about, so maybe, okay, I'll say here, draw again a same graph. I'm going to put a basis vector for the vertices, so I just put 1 on one vertex and a 0 everywhere else. So think about where delta maps a basis vector for r to the v. Okay, so again, there are some orientations here which you have to remember, okay, since that helps determine this boundary map. But now we have a map from the vertices going to the number of edges. It will turn out there's kind of a natural description of it, but I will leave that for you to think about. Okay, so that's all for today. Thanks.